and the Atlantic looks ready for hurricanes. Across broad stretches of the basin, the surface is warm enough to supply the heat and moisture tropical cyclones need. Yet the 2026 season has opened with a very different signal. NOAA's official outlook favors below normal activity. El Niño is expected to strengthen during the peak months, and the atmosphere may become increasingly hostile to developing storms, even while the water remains warm. And that contradiction is the real story. The ocean can hold the fuel while the atmosphere keeps striking the match out. By July 20th, the National Hurricane Center's season summary listed one named Storm Arthur in Tropical Depression 2. No hurricane had formed, and accumulated cyclone energy was running about 19.5% below the 1991 to 2020 normal for that point in the season. On the surface, that sounds like a quiet year confirming a quiet forecast, but July is not the verdict. Most Atlantic activity occurs later, with the climatological peak arriving on September 10th and the busiest stretch generally running from mid-August through mid-October, and the basin still has time to reorganize. The ocean still has time to store more heat, and short-term weather patterns can open or close windows for development long after a seasonal outlook is issued. So the question is not whether the Atlantic is warm, it is whether the atmosphere will allow that warmth to matter. NOAA's 2026 forecast calls for 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes. The agency gives the season a 55% chance of finishing below normal, a 35% chance of ending near normal, and only a 10% chance of becoming above normal. Those numbers do not describe where a storm will go, and they do not guarantee that the desired outcome will occur. They describe the most likely range based on the large-scale conditions forecasters could see before the heart of the season. One of those conditions is unusually important. El Niño is expected to develop and intensify through the Atlantic hurricane season. During the August through October peak, NOAA placed the probability of El Niño at 98%. In the Atlantic, El Niño often strengthens upper-level westerly winds, increasing the change in wind speed and direction with height. That change is called vertical wind shear, and it can tear developing thunderstorms away from the low-pressure center trying to organize beneath them. Warm water builds upward. Strong shear pulls the structure apart. This is why a new ocean temperature headline can be misleading when it is treated as a complete hurricane forecast. Tropical cyclones do not form from sea surface temperature alone. NOAA describes a recipe that also requires a pre-existing disturbance, persistent thunderstorms, abundant moisture, and relatively low vertical wind shear. Water generally needs to be at least about 26.5 degrees Celsius or 80 degrees Fahrenheit, and that warmth must extend deep enough that the storm does not immediately churn colder water to the surface. The threshold is necessary. It is not sufficient. Imagine a tropical wave crossing warm Atlantic water. Evaporation loads the lower atmosphere with moisture. Thunderstorms rise and release heat as water vapor condenses. Pressure begins to fall. Winds start to turn inward, and a circulation tries to close. If the winds above the system are gentle and aligned, the thunderstorms can remain stacked over the center, allowing the system to strengthen. Now change only one thing. Increase the upper-level wind, and the thunderstorm tower tilts away. Dry air can enter the circulation. The warm core becomes displaced from the surface center. Convection fires, collapses, and reforms in the wrong place. The ocean may still be warm enough to support a hurricane, but the atmosphere refuses to let the machine assemble, and that is the hidden battle over the Atlantic. In 2026, NOAA expects Atlantic Ocean temperatures to be slightly warmer than normal, and weaker trade winds can also favor activity. And those conditions usually raise concern because warm water supplies energy, and weaker trades can reduce some of the disruptive forces acting on tropical disturbances. And at the same time, the strengthening El Niño is expected to reverse the early season low SEER tendency and increase hostile winds over the tropical Atlantic and Caribbean. The ocean points one way, and the upper atmosphere points another. Seasonal forecasting is the attempt to judge which influence will dominate often enough to shape the final total. It is not a prediction that every day will behave the same way. A below-normal season can contain a short violent burst. An active-looking ocean can remain quiet for weeks. A hostile atmosphere can briefly relax, giving one disturbance the opening it needs to organize rapidly. That is how storm season can change fast. The phrase does not mean forecasters expect a sudden explosion of hurricanes tomorrow. It means the balance controlling development can shift on weather timescales much shorter than the 6-month season. Wind shear can strengthen or weaken. Dry Saharan air can spread west and later retreat. Tropical waves can become more organized as the West African monsoon evolves. Upper-level ridges and troughs can either ventilate a disturbance or rip it apart. The seasonal outlook sets the background. Daily weather decides the opportunities. This distinction is especially important in July, when many viewers look at a quiet map and assume the danger is passing. Historically, the Atlantic curve rises sharply later in summer. By the peak, systems can form across a much broader area, including the deep tropical Atlantic, where disturbances may have many days over water to develop. And the same warm ocean that seems irrelevant during a hostile period can become much more important if the shear relaxes at the wrong moment. The water does not need to become dramatically warmer overnight. The atmosphere only needs to stop interfering. That is the first major reframe. Ocean heat is not a countdown to a hurricane. It is stored potential. The atmosphere determines whether that potential remains trapped at the surface or is converted into an organized cyclone. There is another reason the title needed correction. June 2026 did produce a genuine heat record, but the strongest verified statement applies to the global extrapolar ocean, not specifically to the Atlantic hurricane basin. And Copernicus reported that the average sea surface temperature between 60 degrees south and 60 degrees north reached 20.860 degrees south. This is the highest June value in its record and 1/100th of a degree above June 2024. That is a real threshold. But it was driven partly by exceptional warmth in the tropical Pacific as El Niño developed, not by a uniform record across the Atlantic. In fact, different parts of the Atlantic can show sharply different anomalies at the same time. A warm subtropical North Atlantic does not automatically mean the tropical main development region is record hot, and a global ocean record cannot be converted into an Atlantic hurricane prediction. The geography matters, the depth matters, the atmosphere matters, and this is why the safer title is also the more interesting story. The Atlantic is warm enough for trouble, but storm season could change fast because the ocean and atmosphere are pulling in opposite directions. And the next question is, what below normal really means for people living near the coast. It does not mean no hurricanes, and NOAA's range still includes up to 6 hurricanes and as many as 3 major hurricanes. Even the lower end of the forecast can contain a destructive landfall, because seasonal totals measure basin-wide activity rather than where storms strike. A season can produce fewer named storms than average, and still be remembered for one system that reaches land at the worst possible place and time. NOAA explicitly states that its seasonal outlook is not a landfall forecast, and short-term and highly variable weather patterns determine where and when a storm affects land. The number of systems across the entire Atlantic does not tell a homeowner in Florida, a port operator on the Gulf Coast, or a family in the Caribbean whether a particular disturbance will enter their region. Risk is local. Seasonal activity is basin-wide. Those two scales are related, but they are not interchangeable. A lower total reduces the number of opportunities for landfall in a statistical sense, yet it never reduces the risk to zero. One storm can pass through an otherwise unfavorable season because the conditions along its individual path become supported. Warm water can help it maintain or increase strength, especially if the upper-level winds weaken and the moisture environment improves. The quiet opening of 2026 therefore deserves context, not complacency. And as of July 20th, the season had produced one named storm and no hurricanes. Accumulated cyclone energy remained extremely low compared with normal. That is an observed fact about the season so far. It is not a forecast for August, September, or October, and the climatological peak is still ahead. And NOAA plans to update the seasonal outlook in early August as the basin approaches its most active period. And that update will incorporate how El Niño is evolving, whether Atlantic temperatures remain warmer than normal, how trade winds and wind shear are changing, and what the early season behavior reveals about the atmosphere. The update could reinforce the below normal forecast. It could also adjust the expected range. Either way, it will not identify individual landfalls months in advance. The strongest documentary image is not a red cone pointing at a city. It is a layered map, and at the bottom lies the warm ocean, visible in orange and red temperature bands. Above it moves a field of invisible winds, some aligned and gentle, others crossing at different speeds and directions. Between them sits a tropical wave trying to build a vertical structure. If the layers line up, development becomes possible, and if they do not, the system is dismantled. That vertical structure explains why surface heat alone cannot answer the season's biggest questions. Hurricanes are tall atmospheric engines. Their thunderstorms rise many miles above the ocean, and the circulation must remain organized through a deep column of air. The temperature map shows the energy source at the base. It does not show whether the upper atmosphere will cooperate. El Niño changes that upper atmosphere. As the central and eastern tropical Pacific warms, the pattern of rising and sinking air across the tropics shifts. In many El Niño seasons, stronger upper-level westerly winds extend across the Caribbean and tropical Atlantic. The resulting shear makes it harder for disturbances to keep their thunderstorms centered and harder for early circulations to mature. This does not make hurricane formation impossible. A strong disturbance may find a pocket of lower shear. A system may develop closer to land in the Gulf or Western Atlantic, where its path over water is shorter but the warning time can also be limited. Another wave may survive dry air and organize when the upper-level pattern relaxes. And seasonal suppression is an average influence across time and space, not an impenetrable wall. That is why a below-normal forecast can coexist with serious preparedness messages. The atmosphere does not distribute risk evenly. It creates windows, and one window may last only a few days, but that can be enough for a disturbance to become a tropical storm. If the water is warm and deep, moisture is abundant, and the shear is low. Intensification can continue, and the same basin that looked hostile on one satellite loop can look dramatically different after the steering and upper-level patterns shift. The phrase change fast belongs here, not in a fabricated claim that the Atlantic has crossed an unprecedented hurricane threshold, and the change is atmospheric alignment. The heat is already available. This also explains why comparisons with recent record-hot seasons must be made carefully. 2 years can have similarly warm water and very different cyclone totals because wind shear, moisture, stability, African easterly waves, and steering patterns differ. Even when one season, the environment can alternate between long, quiet intervals and short bursts of activity. A viewer may see weeks without a hurricane and conclude that the forecast threat was exaggerated. Then the basin can produce several named systems in quick succession. The reverse can happen too. A cluster of early disturbances may create the impression of a historic season, only for the atmosphere to become hostile and suppress later development. Neither snapshot is the whole season. Forecasters therefore track more than the surface temperature. And they monitor the depth of warm water, upper ocean heat content, vertical wind shear, atmospheric moisture, sea level pressure, tropical waves, and in large-scale patterns such as El Niño. They also watch the Madden-Julian oscillation and other shorter-term pulses that can make parts of the tropics more or less favorable for thunderstorms and cyclone formation. Each factor answers a different question. Is there enough energy? Is the air moist enough? Is there a disturbance to organize? Can thunderstorms remain stacked over the center? Will the steering flow keep the system over water or take it toward land? May storm season is the combined answer to all of them. The Atlantic's current warmth therefore changes potential intensity more directly than it changes the number of storms. Warm water can support a cyclone once it forms, and deep ocean heat can reduce the cooling caused by the storm's own winds. But the number of systems that actually organize still depends strongly on the atmosphere. And this is one reason a quiet season can still produce a powerful hurricane. The suppressing factors may reduce the number of successful storms, but they do not necessarily limit the strength of every storm that finds a favorable corridor. And fewer opportunities do not mean harmless opportunities. That is the second major reframe. The season-wide forecast is about frequency and total activity. Coastal danger depends on the specific storms that survive the filters. And by late summer, the most important evidence will appear in operational forecast rather than seasonal headlines. The National Hurricane Center will identify disturbances, assign development probabilities, issue advisories when a tropical cyclone forms, and update track and intensity forecasts as new data arrive. And those products should replace social media maps and isolated model runs. And a single model can show a dramatic hurricane 10 days away and then erase it in the next cycle. An ensemble can reveal whether many model members support development, but even that does not become an official warning. And forecast confidence increases as a real disturbance forms, observations improve, and the event moves into shorter time ranges. The earlier the image, the larger the uncertainty. The closer the storm, the more the details matter. For the public, the useful signals are concrete. Is the National Hurricane Center marking a disturbance? Is the formation probability increasing? Has a closed circulation developed? Are advisories being issued? Is a watch or warning in effect? What impacts are local National Weather Service offices describing? And those signals convert basin-wide potential into a specific hazard. Until then, the most honest language remains conditional. The Atlantic has warm water. NOAA still favors a below normal season. El Niño may increase wind shear. The peak is ahead, and one or more short favorable windows could still produce dangerous storms. All 5 statements can be true at once. The human tendency is to demand a simpler answer. Either the ocean is hot and the season will be terrible, or El Niño is strong and the coast is safe. The atmosphere does not offer that simplicity, and competing forces can operate simultaneously, and the final outcome depends on their timing and location. That uncertainty is not scientific weakness, it is the physical reality forecasters are measuring. Consider the difference between climate and weather. El Niño shifts the background probabilities over months. A ridge, trough, dry air outbreak, or tropical wave changes conditions over days. Ocean temperatures evolve more slowly, storing energy beneath both. The hurricane season emerges from the interaction between those timescales. Climate loads the dice, and weather rolls them. The ocean determines how much energy is available when the roll succeeds. That is why NOAA can predict below normal activity and still warn communities to prepare. The forecast is not permission to ignore the season. It is an assessment that suppressing influences are more likely to outweigh the favorable ones across the basin as a whole. A single coastline does not experience the basin as a whole. It experiences the storm that reaches it. Preparation should match that reality. Residents in hurricane-prone areas should know whether they live in an evacuation zone, understand the hazards that affect their location, review insurance and emergency plans, and follow official local guidance. These are seasonal actions, not signs that a particular landfall is expected. Bigness without invented urgency. No title should imply that a global ocean record guarantees an Atlantic hurricane outbreak. No thumbnail should draw fake Category 5 storm pointed at the United States. No script should convert slightly warmer Atlantic water into certainty about rapid intensification or landfall. And the true story already has enough tension. A warm basin is approaching its historical peak while the strongest El Nino signal in the forecast tries to suppress it. And the season has been quiet so far, but most activity normally arrives later. The ocean can support storms, yet the upper atmosphere may prevent many from forming. If the shear briefly relaxes, the warm water becomes far more relevant. That is a real unresolved contest. In the coming weeks, we'll show whether the atmosphere maintains control. Watch the tropical Atlantic east of the Caribbean as African waves enter the basin. Watch the Caribbean and Gulf for closer to land development. Watch the upper level winds because a disturbance under strong shear can look vigorous one day and collapse the next. Watch the depth of the warm water because a storm crossing a deep warm layer has more energy available than a surface map alone suggests. Another part of the story sits below the surface, and sea surface temperature is the easiest measurement to display, but a cyclone does not interact with a paper-thin layer of water. Its winds stir the ocean, pulling cooler water upward. And if the warm layer is shallow, that mixing can reduce the heat available to the storm. If warm water extends much deeper, the cyclone can continue drawing energy even as it churns the sea beneath it. And this is why forecasters examine upper ocean heat content as well as the temperature at the top. A bright red surface map can exaggerate one kind of danger while hiding another, and two locations may show the same surface temperature, but one may contain a deep reservoir of warm water and the other may cool rapidly when strong winds begin mixing the ocean. The first can support intensification more effectively if the atmosphere is favorable, and the second may look equally alarming on a simple map and then provide less energy than expected. Depth changes the meaning of heat. It also changes how quickly a cyclone can respond when the shear weakens. A developing system that has spent days struggling may suddenly become better organized if it reaches a region with lower shear, greater moisture, and deeper warm water. And that does not mean rapid intensification is inevitable. It means the barriers have changed, allowing the stored ocean energy to become more available to the storm. This is the point where seasonal forecasts and intensity forecasts separate. The seasonal outlook estimates the total pattern of activity over months. An intensity forecast follows a particular cyclone and tries to determine how its core will respond to the environment along its path. And the first can be below normal, while the second becomes urgent. A quiet season can still contain an intense forecast problem, and the location of development matters as well. Systems forming far east in the tropical Atlantic may have many days over water, giving forecasters time to monitor them but also allowing more opportunity for strengthening. And systems forming in the western Caribbean Gulf or near the southeastern United States may have less time over water, yet they can be closer to communities when organization begins. A lower seasonal count does not control which of those patterns occurs. It only changes the expected total number of successful systems. The July 2026 activity illustrates that distinction. Tropical Storm Arthur contributed the season's first named storm energy, while Tropical Depression 2 formed later without reaching hurricane strength by the time of the July 20th summary. Those systems say something about what has already happened, and they do not establish what the peak months will produce. The early ACE number is especially easy to misuse. Accumulated cyclone energy combines storm strength and duration, so a short, weak storm contributes little while a long-lived major hurricane contributes much more. Running far below normal in July therefore confirms that the season has generated little cyclone energy so far. It does not create a protective deficit that future storms must respect. The atmosphere does not keep a balanced account. One long-lived hurricane can change the seasonal ACE total quickly. Several weak systems may raise the storm count while adding relatively little energy. This is why named storm totals, hurricane totals, major hurricane totals, and ACE describe different parts of the season. A headline that uses only one number may miss the actual risk. The same problem appears in heat records. A record for the global extrapolar ocean describes a vast average. It can be scientifically important while saying little about the exact water beneath the developing Atlantic disturbance. A regional anomaly describes departure from normal, not necessarily the absolute temperature. A place can be warmer than average, but still too cool for development, or near average while already warm enough in absolute terms to support a cyclone. Anomaly is not fuel by itself. Absolute temperature, depth, and atmospheric conditions determine what a storm can use, and this distinction prevents another common mistake. Assuming that every warmer than normal patch increases hurricane risk by the same amount. The subtropical North Atlantic, the main development region, the Caribbean, and the Gulf can experience different temperature and wind patterns, and storms also move, crossing from one environment into another. The hazard comes from the complete path, not the color under the center at one moment. That moving path is why forecasts change. A cyclone may be headed toward warmer water but stronger shear. It may enter a moisture region while approaching land. It may cross a deep, warm current just as an upper-level outflow pattern improves. Every new observation updates the balance. The public sees the result as a track cone and intensity number, and forecasters see a changing three-dimensional system. That is also why certainty should increase in stages. Before a disturbance exists, the discussion is about broad environmental potential. Once a disturbance is identified, the focus moves to formation probability. After a tropical cyclone forms, track and intensity forecasts become operational. Watches and warnings appear only when the timing and geographic threat justify them. Skipping those stages creates false urgency. Respecting them creates useful urgency. And for a documentary, the most honest tension comes from showing the transition between stages. The Atlantic begins with enough warmth to support storms. El Niño may keep much of the basin hostile. A disturbance then enters a temporary favorable pocket, and the circulation closes. The forecast problem changes from whether a cyclone will form to how strong it can become and where it will go. That transition can happen quickly, even when the seasonal background remains unfavorable. It does not invalidate the below-normal outlook. Any forecast can be correct about the season and still contain a dangerous individual event. The two statements operate at different scales. This is the point coastal communities need to remember. A forecast of fewer storms is not a forecast of weaker consequences. It is not a forecast for a particular county, island, port, or home. The local danger begins when an actual system and an official impact forecast connect the basin to a place. Until then, preparation should be calm and general. Once that connection appears, the response should become specific and local, and that is how information should escalate. Not from a dramatic temperature graphic directly to a landfall claim, but from ocean conditions to atmospheric opportunity, from opportunity to a disturbance, from a disturbance to a cyclone, and from a cyclone to an official forecast of impacts. Every step requires new evidence. Every step narrows the uncertainty. And every step can move faster once the peak of the season approaches. Most importantly, watch the official forecast evolve. A seasonal number cannot tell you what a specific storm will do. A warm anomaly cannot tell you where a cyclone will form. A quiet July cannot tell you how September will end. The season remains open. There is one final image to hold in mind. Below the Atlantic surface lies a broad reservoir of heat, and above it, invisible winds race in different directions, sometimes aligned, sometimes crossing hard enough to tear cloud towers apart. Between those layers, every tropical disturbance is tested. Most will fail, some may survive. And if one finds warm, deep water, moist air, and a temporary break in the shear, the Atlantic can turn from quiet to dangerous in a matter of days. The ocean has the fuel, the atmosphere still controls the door.